Okay, then welcome to the fifth session of the Isogeny Club. Today we have Boris, and he's a postdoctoral researcher at the LASA group of EPFL, as you can also see from his t-shirt. And previously he was a PhD student in Italy at the University of Roma Tre. And today he will talk to us about torsion point images in SIDH. So he will tell the story of the torsion point images going through their role in the design of SIDH, and then in the design of both adaptive and passive attacks on SIDH. So Boris, the floor is yours.
Hello, everyone. Good afternoon, everyone. Thanks, Chris, for the introduction. So thanks for the invitation as well. I'm going to talk about the torsion points images in SIDH from savior to killer. I hope you can hear me well. If you cannot hear me, then just stop me. You can hear me, right? Right. Okay, so if at any level someone has any question, then you can just stop me, and I don't have access to the chat, so you can just stop me, then I will try to assess your question. If I can, if I cannot, then we will put it for later, and maybe if it's a project we can work on it, then I'll be happy. So let's start. The pointer. Okay, now it's working. So as we all know, isogeny-based cryptography is a very interesting topic today. Why? Because isogeny-based schemes, they have very compact keys, and isogenies are mathematically elegant. Okay, I'm an isogeny, so I can say that, but I'm not sure everyone shares that opinion. The field is quite young, only about 15 years old, some 15 to 17 years old. And the schemes are also relatively slow. So those are the two drawbacks of isogeny-based cryptography. Okay, the two drawbacks before July 2022. So the first key exchange in isogeny-based cryptography was the Couveignes-Rostovtsev-Stolbunov schemes that uses ordinary isogenies. These schemes has two main drawbacks. The first drawback is the fact that on ordinary curves you only have a small amount of smooth torsion. So you cannot build ordinary curves for which the group order, you are assured that the group order will be smooth. And the second problem is the fact that you have a class group action. So ordinary isogenies, for ordinary isogenies, there is an underlying class group action that you use to compute the isogenies. And we know that there exists a quantum sub-exponential algorithm to solve the class group problem, which the class group action on ordinary curves. And this quantum sub-exponential algorithm translates the problem into a hidden shift problem and uses the Kuiperberg's quantum algorithm. So in 2011, Jao and De Feo, they suggested to use supersingular isogenies. Why do we use supersingular isogenies? Because first of all, for the first problem, in ordinary with ordinary curves, you don't have a large amount. You don't usually have sufficient rational torsion points. This is solved with supersingular curves, where you can build your curves with special primes in such a way that you have a sufficient amount of rational torsion point over fp squared. The second advantage is that you don't have any class group action with supersingular isogenies in general. Note that you can also adapt some class group actions on supersingular curves by using some type of orientations. But at this time in 2011, they were not yet aware of that, and we didn't have any class group action on supersingular curves. So those were the two good news, but the bad news is that they don't commute. The isogenies in the supersingular norm, they don't commute. So having a Diffie-Hellman type key exchange with them is not straightforward. But Jao and De Feo, they also had the brilliant idea to use torsion points to solve this non-commutativity issue. So they noticed that if you revealed the images of some torsion points, you could still obtain a commutative diagram, despite the fact that supersingular isogenies, they don't commute naturally. So with this, everything was good till 2016, when SIDH was submitted to the NIST competition. So when SIDH was submitted to the NIST competition, we had the first cryptanalysis result, the first important cryptanalysis result on SIDH, which was the GPST adaptive attack on SIDH in 2016. So this was the first attack on SIDH, and it really exploits the fact that there are torsion points images in SIDH. Until today, there is no non-countermeasure to this attack, and the only countermeasure, practical countermeasure, is the generic one, which is the Fujisaki-Otamoto transform that is used in SIDH. Okay, that was used in SIDH till July to obtain a CCA secure key encapsulation mechanism. Next was the first non-trivial classical passive attack on SIDH introduced by Petit that had no impact on parameters, on SIDH parameters suggested by Jao and De Feo and parameters used in SIDH. This attack was later improved in 2021, still by Petit and some co-authors. The range of parameters to which this attack applies was increased, but still the attack did not apply to SIDH parameters. In 2022, Christophe and I, we suggested a new adaptive attack on SIDH that were using a Petit torsion points attack as a subroutine. Still, it had no impact on SIDH. But in July 2022, we had the final shot where Kastrick and the crew, they suggested an attack on SIDH, which was using the torsion points images as well, but also required the knowledge of the endomorphism ring. Oh, I forgot to add the other citations. The same ideas were suggested by Minor Martindale in the case where the starting curve has unknown endomorphism ring with a sub-exponential attack proven by De Feo. But few days later, Robert showed that by going into higher dimensions, you can have a polynomial attack. So I forgot to include the Minor Martindale and Robert citation there. And all these attacks, they use torsion points. So all the cryptanalysis on SIDH, or the, not say all the cryptanalysis, but all the attacks that really affected SIDH or SIDH with some overstretched parameters, they really relied on the availability of the image torsion point images in the public key. Note that this list is not exhaustive because there is also a paper, I think by Tonelli, or these are authors from the Israel Corporation in Canada. They also have a paper on torsion points attack where they use endomorphisms with a large eigenspace. With large eigenspaces. I didn't put this in the list because it doesn't really fit in the framework that I will show you later. But this paper also considers a torsion points attack on SIDH. Okay, describes attacks that also uses torsion points. So with this, we will now dive into our presentation, where the first thing will be to first present the role of the torsion points in SIDH. Why do we have torsion points in SIDH? We will briefly describe the GPST adaptive attack. We will then describe the general framework for torsion points attack, and we will show that the Petit torsion points fit into this framework, and that the Damien-Robert attack, which is either inspired from the Kastrick-Decoux or a generalization of the Minor-Robert attack, the Minor-Martindale attack, fits also into this framework. And if we have some time, we will briefly talk about the new adaptive attack that we presented, that we published last year or earlier this year. So let's start with the rules of torsion points attack in SIDH. Before that, we recall that if you take an analytic curve defined over FQ, then the end torsion is a free group of dimension 2. With supersingular curves, they have an endomorphism ring of dimension 4. They are always defined over FP squared, and we have that their cardinality over FP squared is either Z over P plus 1 Z square or Z over P minus 1 square. This is why you can easily control the order of supersingular curves and hence have a large amount of smooth torsion defined over FP squared. Because if you choose P such that P plus 1 or P minus 1 has a lot of smooth, the smooth part is large enough, then you will have exactly this smooth part will correspond exactly to your smooth torsion defined over fp squared. You have supersingular cyclic isogenies, they don't commute in general. And if you take a supersingular D isogeny, then kernel can be represented in the form P plus alpha cure, where P and cure is a well-chosen basis. Note that if you fix the basis beforehand, then not all kernels can be represented this way, but in general, a good fraction of them can be represented this way. I think at most more than one half of the isogenies. So if you have an exponential number of isogenies, then more than half of them can be, the kernels of more than half of them can be represented this way. So with this, we can now describe SIDH. So as we said before, isogenies, supersingular isogenies, they don't commute. So if you would have been thinking that we could just start from a curve E0, compute two random isogenies, then try to recompute the push forward of these isogenies or similar isogenies from the n curves and obtain the shared curve, then this would not work because, as we said before, they don't commute, and it is not even clear how you will compute these follow-up isogenies, phi A dash and phi B dash. So Luca and Jao and De Feo, they suggested to reveal torsion point images through the secret cyclic isogenies such that you can carry the kernel of your blue isogeny phi B to the curve EA just by looking at the images of these torsion points that will form a basis of your n torsion if you are considering n torsion points, or of your NA torsion if you are considering NA torsion points. So how do you do that? You choose P of the form NA NB minus 1. Then your supersingular curves will have order P plus 1 square, and P plus 1 here will be NA times NB. Then you choose your basis PA and QA for the NA basis, PB and QB for the NB basis. Then you can reveal the image of your torsion points through your basis, and then each party can then push forward, compute the push forward of the kernel of his secret isogeny by using just linear algebra facts, where if your kernel was generated by P plus alpha cure, then the kernel from the other curve will be generated by the image phi B of P plus alpha phi B of cure. Using that, you can then compute the exact push forward of your secret isogeny and hence get a commutative diagram. So when you have SIDH, the first problem you face is how do you validate public keys? In 2016, I think a paper by Costello and some co-authors suggested that we could use pairings to eliminate some trivial adaptive attacks on the scheme. Note that pairings, they only help you to like verify up to some degree the compatibility, that the public keys are somehow compatible, but they don't like tell you that the public keys were well computed. And this is why you will see that this validation does not validate the key correctly. It only tells you that the key is somehow conform with the pairings, but it is not a tool to validate public keys in SIDH as one would like to validate them. So in SIDH, what is the underlying hard problem? Here you have the supersingular isogeny problem with torsion point information, where you are given the starting curve and the end curve and the action of the secret isogeny on some torsion points, and you are asked to recover the secret isogeny. So that is SIDH, and we'll move to the GPST adaptive attack on SIDH. We'll give an overview of that attack and the principle of the attack. So do we have any question up to here? I believe no, because at the Isogeny Club, I think presenting SIDH may be even losing some time. But do we have any question? Not yet. Okay. So the GPST adaptive attack, how does it work? So at the beginning, you suppose that you have access to some oracle, O of E, RS, E dash. Here, ERS is like stands for your public key. So you have a certain public key and you have another curve, E dash. And you want to see if when you give this public key ERS to a party that owns an honest secret key, what is the curve that this party compute? Is this curve equal to E dash? So if you are Bob, that is the second party in the key exchange, and the honest party is Alice, and this Alice is using a static secret key, and Bob computes some number of public keys that here are represented by E, R, S. Note that E is his curve, R and S are the images of the torsion points. And then he chooses another curve, E dash, and he wants to know if E dash is the curve obtained by Alice when she uses this public key as Bob's public key. So the oracle will return 1 if the answer is yes, and the oracle will return 0 if the answer is no. So suppose that you have access to this type of oracle with which Bob can check if the given curve is the shared secret of an SIDH instance or not. Then the idea of the attack is to use public keys in which you add some well-calibrated noise in the torsion point images. By well-calibrated here, I mean the point should be well chosen in such a way that the attack should be effective. And then you use the key, when you add this well-calibrated noise in the torsion point images, you use the key exchange oracle to determine if the noise is cancelled when Alice or when the honest party is computing the shared secret or not. If this noise is cancelled, then you can, or it is not cancelled when you learn this information, you can deduce 1 bit of the secret scalar alpha of the owner of the secret key. So adding noise here is just multiplying the torsion point images by the well-chosen scalar. So how does this work in practice? Okay, that was slow. So in practice, the first step consists in recovering the parity of the secret scalar alpha. So for that, the matrix you will use to put the noise in the torsion points will just be this matrix M1 that you can see from the screen, 1, 2 to the A minus 1, 0, 1. And you can see that the malicious torsion points images here would then be R1 equals to phi B of PA and S1 equals to phi B of QA plus a small noise that here has, I think the order is 2. So you see that here we are, for the first step, you add a small noise of order 2. And you can notice that the oracle will return 1 when the shared curve or the shared secret will be equal to the curve that Bob computed, or because Bob here we use the curve E prime when he queries the oracle here. He replaced the curve E prime by the curve that he gets when he honestly completes the key exchange from his side. Then he would check if Alice also gets the same curve, but with his malicious torsion points or with his torsion points in which he has added some calibrated noise. So if he checks, if the oracle returns 1, this means that the kernel of the isogeny that Alice computed is in fact the kernel of the isogeny that she ought to compute in a normal SIDH instance. And this translates to alpha times S1 is alpha times phi B of QA. And if you look at S1, you will see that it means that alpha times 2 to the A minus 1 was in fact 0. This means alpha was even because we are considering the points modulo 2 to the A. So this is how you can learn the parity of alpha. Then to continue the attack, you can easily show that if you use this matrix MI, then the oracle will return 1 if and only if the bit that you are attacking at that moment is 0. And if it doesn't return 1, then that bit was 1. So this is how the GPST attack works. And the only known countermeasure to this is the FO transform, I think. Oh, I didn't add that. I thought I added that. So the only known countermeasure to this is using the FO transform. We had a suggestion of a countermeasure last year, but this was later proven to not be secure by ourselves and by Galbraith and Yifu independently, I think. So that's all about the GPST attack. I don't know if anyone has any question. Not yet. Okay. Is it very clear or is instead very dark? Because when there is no question, then usually it's at the extreme. Either it's too clear or it's very hard. Like,
I think you're still being clear.
okay. Let's hope it will be clear to the end. So now let's move to the framework for torsion points attacks. This is, or I should have clarified the framework for passive torsion points attack, because what we have just seen is still a torsion point attack, but it is an active torsion point attack. So this, now we move to passive torsion points attack before coming back to active attacks later, because the active attack that we present later needs, for that one, you need to know the torsion point attack first, or the classical torsion point, the passive classical torsion points attack first. So more fact about isogenies. If you are given a separable degree D isogeny from E to E prime, then there exists the dual isogeny from E prime to E that has the same degree, and such that the composition is just the integer, the scalar multiplication on the respective curve, depending on how you compute the composition with the two isogenies. So when you have an isogeny phi, you can recover the kernel of its dual just by evaluating phi on the D torsion. If the isogeny phi has degree D, then you can recover the kernel of the dual by evaluating phi on the D torsion. And you can also recover the kernel of phi by evaluating phi dual on the corresponding D torsion on the N curve. So what does this mean? It means that to recover an isogeny, it is sufficient to evaluate it on the D torsion, where D is the degree of the isogeny. This will be very important when trying to implement classical passive torsion points attack. So to recover an isogeny of degree D, it suffices to evaluate this isogeny on the D torsion. So recall that here we are targeting the supersingular isogeny problem with torsion point information. The first general step that you can always identify in classical or passive torsion points attack is a sort of degree transformation. So you have an isogeny of degree, let's say here, what did I choose the degree to be? Okay, I think here the degree will be NA, as in the SIDH. So you have an isogeny of degree NA. If you could evaluate this isogeny on the NA torsion, then you will recover the isogeny. What you have is that you don't have the action of the isogeny on the NA torsion, but you have its action on the NB torsion. So this degree transformation is a sort of transformation where you use your isogeny of degree NA to build an isogeny of degree NB that you can evaluate. So I use my isogeny of degree NA, I build an isogeny of degree NB that I can evaluate, and this isogeny here is denoted by tau. So I use a map gamma that is always that you can see from the context, that it can always be extracted from the context of your attack. You can use this gamma to obtain an isogeny that depends on your secret isogeny phi and some input that are explicit from the context, and that when you evaluate, or when you extract this gamma, you will get something which is tau, which has degree, usually not NB, but in the best case, it should be NB, because you have the action, you know the action of your phi on the NB torsion. So you would like to have an isogeny that you can evaluate on the NB torsion. So in the best case, the degree of tau should be B, or NB, sorry. But we can see that, we will see that even when it is NB squared or NB squared times some small integer, you can still get away with it. So what do you want? You want that when you know tau, you should be able to recover your secret isogeny phi. As I said, you should be able to evaluate the isogeny on the NB torsion. Then you should be able to recover the isogeny from its action on the NB torsion. So it's not every isogeny that you evaluate on the NB torsion that you can always recover it. For example, you know the action of phi on the NB torsion, but you cannot recover it. So this is where the fact the degree of tau should be like NB dependent. So if you have this sort of degree transformation, then you can run the attack just by, first of all, you find your correct tau, you evaluate your tau on the NB torsion. And since we said that when you can evaluate an isogeny and from 0.3, I want to say, since you use 0.3 to recover your tau from its action on the NB torsion, and when you recover tau, you use 0.1 to derive your phi from tau. So maybe I repeat this again. You have an unknown isogeny phi. You first do a degree transformation to obtain an isogeny of degree NB. You evaluate it on the NB torsion. You recover this isogeny from its action on the NB torsion, and then you use this isogeny tau now to recover your secret phi. So how does this work in the case of Petit's attack and improvement? What is the gamma that you use here? So in the Petit's attack, you assume that you know the endomorphism ring of the starting curve, and your input, recall that we had this phi and some other input that you give to your gamma. So here, your input is theta, which is a special endomorphism of the starting curve E0, because here you are assuming that you know the endomorphism ring, and some integer d. And then you define your gamma of phi theta d to just be the endomorphism phi dual composed with theta composed with phi plus the scalar multiplication by d. This is an endomorphism on E, because you start from E, you go through phi dual, you do theta, is the endomorphism theta on E0, then you come back to E with phi, and then you add an integer, a scalar multiplication d. So this gives you an endomorphism tau on the curve E. So when you have this endomorphism tau on the curve E, it means you have which has degree n squared times E. Then it is proven that you have a good setting for you have good parameters for your torsion points attack. And you can prove that, you can easily see that they verify the three conditions that we stated before. Knowing tau, you should be able to recover phi. Tau can be evaluated on the NB torsion, and tau can be recovered from its action on the NB torsion. So for the first point, you can just see that tau is d plus an isogeny that factors through phi dual. It means that if you do tau minus d and you evaluate it on the NA torsion, you should be able to recover the kernel of phi dual, right? Because the kernel of phi dual is included in the kernel of tau minus d. So if you do tau minus d and you evaluate it on the NA torsion, then you should recover the kernel of phi dual. So when you know tau, you can recover phi just by evaluating tau minus d on the NA torsion. For the second point, can you evaluate tau on the NB torsion? Yes. Why? Because you know the action of phi and phi dual on the NB torsion. You know theta and you know the scalar multiplication by d. So I can evaluate phi dual on the NB torsion. I can evaluate theta because I know theta. I can evaluate phi because I know its action on the NB torsion. So I can evaluate tau on the NB torsion. The next point, can you recover tau from its action on the NB torsion? Here, if tau was an isogeny of degree NB, then we would just apply what we said before. But here, tau has degree NB squared times E. Note that in the very first paper by Petit, I think tau there had degree NB. His aim was to have tau, was that the degree of tau should be NB. And that was why there was a large distance between the parameters for which the attack applies and the normal parameters in SIDH. But here with degree of tau being NB squared, you reduce the gap a bit. So let's see how, when the degree of tau is NB squared times E, how you can recover the isogeny tau from its action on the NB torsion. Is there any question? No, everything is clear. So degree of tau is NB squared times E. It means you can factor tau as the composition of three isogenies. psi1 times psi e times psi2 dual, where psi1 has degree NB, psi2 has degree NB, and psi e has degree A. Psi1 has degree NB. Since you know the action of tau on the NB torsion, you can recover the kernel of psi1 by evaluating tau on the NB torsion on E on the curve E. So you can recover the kernel of psi1 by evaluating tau on the NB torsion of E. You can also recover the kernel of psi2 by evaluating the dual of tau on the NB torsion on E. So this is where you play with the NB square factor. So you can recover the kernel of psi1, but you can also recover the kernel of psi2 just by evaluating the dual of tau on the NB torsion. So with this, when you recover psi1 and psi2, all you are left to recover is psi e. But psi e has a small degree E. So you can just do this by brute force, and you hence recover tau. You hence recover the full kernel of tau, and then you know tau. Okay, for everyone? I believe so. So the thing now is like, how do you find these parameters theta and d such that the degree of tau is exactly NB squared times E, where E is small enough? They are easy to find. In fact, in the paper by De Couveignes, Fouotsa, Leonardi, and other co-authors, they prove that they are easy to find when NB is greater than P times NA. So here you still need the parameters to be in balance. And in SIDH, by that time you had a NA which was roughly NB and which was roughly square root of P. So this was not, you could not apply this to SIDH in 2021. So I think this concludes this part on the Petit torsion points attacks. Any question? No? No? I don't know if I should be happy or if I should be sad, but I think I should continue. That's the aim. So now we move to the higher genus thing now, things that are hot topic. So let's see how we can fit this attack into the framework that we discussed before. So I would like to say this fitting this into the torsion points attack, the already known torsion points attack framework is not from me. So it's from, I think Lawrence had a blog post about it, and it is also already in the paper of Damien. So you can also refer to that paper if you want more details about this version, this description of the attack. So here you assume that your final house degree, your secret isogeny has degree NB, because in higher dimension, it is rather better to have torsion points of order a power of 2 rather than a power of 3 or something else, just because in the attack, you need to evaluate some NA isogenies. So it's better that NA should be a power of 2. So it's better to attack Bob's isogeny here. So your secret isogeny has degree NB, and your torsion points, they have order NA. You set A to be NA minus NB, that you write as the sum of 4 squares. Every positive integer can be written as the sum of 4 squares. So you write your NA minus NB as the sum of 4 squares, A1, A2, A3 plus A4 all square. Then your gamma now is this endomorphism that you choose on in higher dimension. So just see this as the product of what we know normally, if you don't know abelian varieties as me as well. So you just see this as the product. You can just look at it as R to the 4th times C to the 4th as we see things. So this product is just, you can see it like that, but even though it can be more complicated than that. So when you look at this gamma, you can easily see that gamma is an endomorphism on this product. So alpha here is just an endomorphism on the 4 copies of E0. which is represented by this matrix M. Alpha B is the same endomorphism, but instead of on 4 copies of EB, which is represented by the same matrix. Then the phi times identity 4 is just the endomorphism on, not the endomorphism, but the isogeny on 4 copies of E0 to 4 copies of E1, which is diagonal. So you just take the same. If you have a point P, 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 you send it to phi of P, phi of, if you have a point P, Q, R, S, you send it to phi of P, phi of Q, phi of R, phi of S. So it's just the diagonal isogeny. So when you have your secret isogeny phi, you can consider these secret diagonal isogenies, phi identity 4 and phi dual identity 4, that go from the 4 copies of E0 to the 4 copies of EB, and the dual that goes from the 4 copies of EB to 4 copies of E0. So when you have all of these, then you can build the matrix tau, which is gamma of phi and A, which is in fact the endomorphism of that abelian variety. So one clear fact that you can see here just by construction is that the degree, which you can just see as the determinant, which you can recover just by looking at the determinant of this matrix, is exactly NA. So if you try to compute the degree, you will see that the degree is alpha 0 times alpha beta square. Note that if you want to write in the matrix notation, alpha 0 and alpha beta, they have the same matrix notation. So when you take the dual, just by multiplying, you will get something which is like the determinant, and that is exactly A, because we wrote A as the sum of 4 squares, and we choose this matrix M such that just by multiplying that we get A. And then if you multiply the phi and phi ID4 and phi dual ID4, then you get the degree of phi, which is NB. So which is NA, is it NA or NB here? Okay, which is NB, and then you would then get, is there a minus somewhere here? Maybe there was a minus and I didn't put it. I think there is a minus on the dual here that I didn't put, sorry. I think there is a minus on the dual. Then you would then get the degree, that is NB plus NA plus A, that gives you NB. So now you have an endomorphism on this abelian variety that has degree NA. You can evaluate it on the NA torsion, right? So we will look at the properties. The first property was, okay, we will start by the second one, which is more straightforward. So the second property is you can evaluate it on the NA torsion. So if we come back, we can evaluate phi and phi dual on the NA torsion, and the endomorphisms alpha and alpha B dual are just scalar multiplications or linear combination of scalar multiplications on some specific curves, so they can be easily evaluated on any torsion point. Phi and phi dual, you know its action on the NA torsion, so you can also evaluate that diagonal isogeny on the NA torsions. So you can evaluate tau on the NA torsion. So the second point is okay. The third point, tau can be recovered from its action on the NA torsion. Tau has degree NA, so it can be recovered from its action on the NA torsion without any problem. Then, knowing tau, you should be able to recover phi, or phi, sorry. My French is impacting, it's like colliding with my English. So knowing tau, you should be able to recover phi. It can be seen just from the representation of tau, that if you know tau, then just by evaluating it on some specific points, let's say you set the first point to be anything, and then you look at what happens on the 4 last points, that is the 4 last points on the second on the 4 copy of EB, then you can recover the kernel of phi dual. So if I evaluate it on a point P1, P2, P3 till P8, then I just look at what happens to the 4 last points, then I will get the kernel of phi dual. So with this, it means your 3 conditions are like satisfied. What do you need here? As opposed to the Petit torsion points attack, there is no condition on any parameter here. The only input is A. and you have everything follows immediately. So you don't have any requirements on the inputs of the algorithm here. So everything just runs in polynomial time. Note that it is more complicated than this, but this is like the high-level description of the general of the attack. So it runs in polynomial time. It breaks SIDH, it breaks SIG, it breaks theta, it breaks everything that uses torsion point images. So do we have countermeasures? Not really yet. We have some ideas and they are still like being investigated. Any question at this point?
Yeah. How does this affect p-side, for instance?
How does this affect
p-side from
p-side
Antonin?
from Antonin? So in p-side, you are revealing images of some endomorphisms, right? You are revealing the push forwards of some small endomorphism in some subring. But the push forward that you are revealing are through, they are images through an isogeny of prime degree. So I don't know how this will really affect that. I have not like investigated if this really affects that, but I think there is already one thing that should be taken into account, the fact that the secret isogenies there, they have prime degree, which will be something that, so what do you call secret key there then? If the isogeny has prime degree, you cannot like, to evaluate the isogeny, you need to know the endomorphism ring of the starting curve. So I'm not really, I don't see how they apply trivially, because maybe if you want to apply them to p-side, then you need a bit more work. I'm not sure, but the secret isogeny has prime degree. It's just an ideal of prime norm. So I'm not sure they trivially extend to p-side, or maybe I'm missing something, but I'm not sure they trivially extend. If they apply to c-side, then maybe you need some little tricks or.
Okay, thanks.
Okay. So if it's all good, as I said, you can already find this in the Damien's, in the current version of Damien's paper, and in a blog post by Lorenz Pani. So if this is good, then we move to the adaptive attack, which was a previous result before the Gastric de Croo, minor martingale, and Robert attacks. So in this adaptive attack, as opposed to the GPST adaptive attack, where you learn the bits of the secret alpha one by one, here we try to use the torsion point attacks. So recall, with the petit torsion points attack, they did not apply to SIDH, because in order to apply them to an SIDH instance, you need NB to be greater than P times NA, while in SIDH you have NB, which is roughly NA, and equals to N to P squared, equals to square root of P, sorry. So what you need is like P, the amount of torsion points you need more is P. You need like a P torsion, the action of the secret isogeny on roughly P torsion, to be able to apply the attack. So the general idea of the attack is to use the key exchange oracle to recover the action of the secret isogeny on new torsion points of order roughly P. And then in that case, you will now have an SIDH on which you can apply the petit torsion points attack, and then you just run the petit torsion points attack to recover the secret isogeny. So here you suppose that you have your key exchange oracle as before, and then the attack just proceeds in two phases. The first phase, you like actively recover the action of the secret isogeny phi A on more torsion points. Here we don't really recover the action of the isogeny on torsion points, but we recover it on torsion groups. And in general, when you can recover the action of an isogeny on 3 cyclic disjoint torsion groups, then you can use this action to recover the image of any group of the same order. So when you recover the action of the secret isogeny on torsion groups, then you can now apply the petit torsion points attack. So note that with the petit torsion points attack, as far as you have the action on torsion groups. Even if you don't have the action on torsion points exactly, you can run the attack easily. So what we are going to discuss here is mainly the first part: how do you recover the action of the secret isogeny on larger torsions, on larger torsion points using the key exchange oracle. Is it good for everyone? Okay, I still have 12 minutes. I think I can do that. So the second part, we already know how to do it, running petit torsion points attack. So how do we recover the action of a secret isogeny on a larger torsion group? So I want to recover the action of my secret isogeny on a group of order n, where n is the product. N should be power smooth. You will understand why n is power smooth later. So n should be the product of some li's. Here we choose li's to the squares, and then n is coprime to na and nb. So what I want is to recover the action of the secret isogeny on the L torsion. So I pick one of the L dividing n. Then I choose a random cyclic group G of order L squared times nb. Note that I know the action of the secret isogeny on the nb torsion. Now I want to recover the action of the secret isogeny on the L squared times nb torsion. So when I pick a group of order L squared times nb, this group contains, if the group was cyclic, then it contains a unique subgroup of order nb, which represents an isogeny phi b. You can, of course, run the SIDH key exchange with this subgroup as your secret group, and then you will get this square, which is described on the board. But now I have a group of order L square nb. So normally, if I want to use this group, there will be another isogeny that continues from EB to a curve EG. And what I want to know is, in fact, the push forward of this second part of the isogeny through the secret isogeny. So I want to know what isogeny down from EB corresponds to the image of this, or to the push forward of this isogeny through the secret isogeny. How do you do that? Since L, we choose L n to be power smooth, it means L square is in fact of polynomial size. So you can like compute, since Bob can like run the normal SIDH key exchange with EB, it means he can recover the shared curve. When he recovers the shared curve, he computes all curves that are L square isogynous to this shared curve. He knows that one of these curves is exactly the shared curve that Alice would obtain if she had used the curve EG as the public key of Bob. So Bob first does the key exchange with the curve EB to obtain the curve EAB, and now he uses the public key EG and torsion and the correct torsion points as public key in a new key exchange, and he checks if he picks all curves that are L square isogynous to EAB, and he queries the key exchange oracle with these curves. So what he will get is, he takes the public key EG, RS, where RS are like computed this way. I will explain why they are computed this way. And then he takes a curve EH, which is L square isogynous to EAB, and he queries the oracle with this tuple. If the oracle returns 1, it means the curve EH is the curve that Alice computed, and hence the isogeny from EAB to EH is the push forward of the isogeny from EB to EH. And he hence learns the image of the kernel of that isogeny through the secret isogeny. So with this, he can then query many as much as E isogenies like this, or he can use E SIDH squares like this to get the all the information he needs. And then with that, he will get the action of the secret isogeny on the N torsion. So why do we need N to be power smooth here? Because when you take points of order L squared times NB, or just order L squared, in general, they are not defined on FP square. They are defined over an extension whose degree is at most the order of the point. So when you take n to be power smooth, it means you are sure that your points will be defined over a degree, over an extension whose degree is not that much large. Now, why do you scale R and S by L by the inverse of L modulo NA? Because the isogeny phi j has degree L squared times NB. So if you compute the pairing, as we said in the SIDH that there is a pair, you can do a pairing check. With this isogeny, then the exponent that will come out in the pairing will be L squared times NB and not NB, because Alice knows that your secret isogeny has degree NB. If she computes this pairing and then the exponent is not NB, then she would detect it easily. So the real exponent is L squared times NB. And to remove this exponent, you scale the points by L minus 1. And then the L minus 1 square will come out when she will be computing the pairing as well. And it will erase the L square factor in the degree of the isogeny. So with this, you can repeat this many times, and then you get the action of the isogeny on more torsion points. And when you have the action of the isogeny on more torsion points, you now run the petit torsion points attacks. Is it clear for everyone? Okay, no question, then I think we are on time. So how can you counter this? Okay, normally you cannot counter it because you have constricted crew and everything, which like boils everything down to 0. But at that time, you could just choose a random starting curve with unknown anamorphism ring, or just use the FO as it is used in psych. So this brings me to the end. But before we end, let me summarize. So we have seen that torsion points have caused the death of SIDH. Is the one question that one can ask is there any hope for countermeasures? We have there have been 2 ideas, one by Moria, in which the one by Moria consists in masking the degree. So it's a sort of SIDH with non-fixed degree. And another one is by me, consisting in fixing the degree, but just having torsion points of smooth order, and then revealing the images of torsion points up to a scalar. With the current analysis, it shows that we need primes of at least 6,000 bits. So it's not a good news, of course. And this Ryan as well, they are still vulnerable to adaptive attacks. And so even if you wanted to build a chem with it, you will still like need the FO which will make things even worse. So for more details about this, I think we have there is a video of a talk at COSIC, I think, and there is a talk in the upcoming weeks that I'll be giving in Rennes. So maybe you can also come to that talk to see what I have to say, or if there is more update about the countermeasures. So I think I will stop here. The time is, oh, I did a good run. So I am happy to discuss any comments you may have.
Yeah, thanks a lot, Boris.
Thank you.
If anyone has any questions, you can just unmute or write in the chat. Yeah, so maybe I can ask, it was maybe not the main topic of your talk, but these countermeasures, do you believe that they will be the savior of SIDH or schemes that use torsion points, or do you think they remain mainly theoretically interesting?
They are interesting, but since with the recent attacks, I don't want to be that much confident, but I think they are interesting in the way that you don't really reveal the exact images. But the fact there have been some analysis result that really prove that one should be careful, because at the beginning we had parameters of 3,000 bits, I think, but then we noticed that there are some tricks that you can always like use to like reduce the security of the scheme. So I think they really need to be analyzed. And yeah, but for now, I think the analysis that has been done is already sufficiently good, and we have some confidence. But the fact that the parameters are very large also is 6,000 bits is a bit discouraging for isogeny-based, but I think they are promising, and yeah, they need to be looked into. Maybe someone will also come with a new countermeasure idea. So I think, but what I see is like the more we're trying to counter SIDH, the more it brings it closer to C-side. It seems like if you really want to counter it, then you should really move towards C-side, like or oriented things or something like that. The more you want to counter it, the more you feel like you should move to C-side or yeah. One good thing is that if you really find a stable countermeasure, then you will need to compare it to C-side, because on C-side you have sub-exponential attacks, quantum attacks. If you find a quantum measure that with good analysis is still better than C-side, then I think it's still interesting in some sense.
Yeah, good point.
I was wondering if you're sorry.
I was
if you still want to add something, go for it.
Go on.
No, go on.
Okay, I was saying that I wanted to say that the fact that you still have adaptive attacks is also a good point for SIDH, for C-side, right? So the fact that even with the countermeasure you still have adaptive attacks is still like a good point for SIDH, that it will be hard to like take it will be hard to beat that. I think no matter what type of countermeasures you come with, as far as it is not C-side, you have adaptive attacks. So that is also, because if you don't have adaptive attacks, then it means there is like a trusted way to verify the public key validity somehow, like, yeah. And validate SIDH type scheme, validate the public keys in SIDH type schemes is a really hard problem, I think. Maybe even equivalent to breaking the scheme itself, probably. Maybe, I don't know, I'm not sure, but
yeah.
So I was wondering about this last new adaptive attack that you presented. Is it applicable then to every set of for every size of NA and NB, or are there still restrictions on it?
You mean the adaptive attack on the countermeasures?
No, this new adaptive attack that you presented with this prime L times NB.
Yes. What was your question again? Sorry, about the attacks.
So what are the restrictions on NA and NB for this to work?
No restriction. In fact, as far as you are in an SIDH instance, you don't need any restriction, because no matter what restriction you have, you can always, no matter what the NA and NB are, you can always actively get more points or more torsion. So even if you didn't have NB, but you are still in an SIDH, then you will create NB yourself. Like you will choose your N, and then you will recover the action of the secret isogeny on the torsion. So there is no restriction on the size of NA and NB. It's an adaptive attack, so you suppose that you have access to some key exchange oracle. So with this oracle, you can always recover as much torsion points as you want, or as much torsion point images as you need. So even if NB is smaller than NA or square root of NA or anything, as far as you are in an SIDH setting, you can recover as much torsion points as you want or as you need for the attack.
Can I ask a follow-up question? Like compared to GPST, I guess you typically need fewer oracle calls, or
no, it needs more oracle calls.
No, okay.
Because you have like you see here, you will need like many LIs, and then for each LI you will need to query to do L square queries, like roughly L square, not roughly L square queries in the worst case, and then
okay,
and then I think for each you also need to do it 3 times, because you have 3 groups, 3 secret. You need the image on 3 cyclic disjoint groups of order L. So you do this 3 times. So there are more queries than in the GPST attack where you only have a lock of NA queries.
Right, yeah, you're right. It's clear now.
But it's still a polynomial number of queries, of course.
Yeah. Okay. Yeah, thanks a lot, Boris.
Thanks for the invitation.
Yeah, no, thanks for coming. I'll stop the recording now.